Ampere's law in differential form. We have already studied Ampere's law in its integral form, and we said that the integration of the magnetic field over a closed loop equals the current passing through this closed loop. So to obtain the equivalent Ampere's law in differential form, we are going to simulate a simple problem including differential element delta x delta y, which is making a differential surface area delta s, and we are going to assume the magnetic field at the center of this differential loop is hx naught at x direction plus hy naught at y direction plus hz naught at z direction. Now we are going to perform Ampere's law in its integral form. So the magnetic field H dl over this closed loop would equal the current passing through this loop. Okay? So assuming that we are going to integrate along this closed path from 1 to 2 and from 2 to 3, from 3 to 4 and from 4 to 1. So the integration over the closed path can be divided into 4 parts. The first part is from 1 to 2. Along the path from 1 to 2, the delta L is directed along the direction y. So H dot dl in this case will be simply the y component of the magnetic field multiplied by the length delta y. But the magnetic field at the arm 1, 2 is not the magnetic field at the center, because we already have moved along the x-axis by a distance equals delta x over 2. So the magnetic field along the path 1 to 2 by using Taylor series can be obtained as the magnetic field at the center hy naught plus the derivative of hy with respect to x multiplied by delta x over 2. So in this case, hdl along the path 1 to 2 would be hy naught plus half the derivative of hy with respect to x multiplied by delta x, or in other words, the derivative of hy with respect to x multiplied by delta x over 2, which is the distance we have moved, and this multiplied by the value of delta L in this case, which is delta y. So this is the integration of H dot dl along the path 1 to 2. In a similar way, we can obtain the integration along the path from 3 to 4. But in this case, delta L would be delta y in negative y direction, not in positive y direction. So it would be negative delta y. And the magnetic field here would be hy at x equal minus delta x over 2 from the center. So along the path 3 to 4, the magnetic field would be, or H dot dl would be hy naught minus of the derivative of hy with respect to x multiplied by delta x multiplied by minus delta y, not delta y, because here along the line 3 to 4, the direction is in negative y direction, not in the positive y direction. Okay. In a similar way, we can obtain the integration along the path from 2 to 3. In this case, delta L is delta x in negative x direction. So H dot dl would contribute only to the x component of the magnetic field. And the x component along the path from 2 to L equal the x component at the center plus the derivative of hx with respect to y multiplied by delta y over 2, because we have moved the distance delta y over 2 from the center until we reach the path from 2 to L to 3. Okay? So the integration along the path from 2 to 3 h dot dl would be negative, because we are talking about negative x, not positive x, negative delta x multiplied by hx naught plus the derivative of hx with respect to y multiplied by delta y over 2. In a similar way, we can obtain the integration along the path from 4 to 1. In this case, the direction of delta L is delta x. So it would be positive delta x, not negative delta x. And we are going to introduce or to use hx, because we are talking about delta L in x direction. So it would be hx at the path from 4 to 1. hx at the path from 4 to 1 would be hx at the center minus delta y over 2 multiplied by the derivative of hx with respect to y. So the integration over the arm from 4 to 1 would be, instead of negative, it would be positive hx naught minus half the derivative of hx with respect to y multiplied by delta y multiplied by delta x. Okay. So this is the integration of h dot dl from 1 to 2. This is the integration of h dot dl from 2 to 3. And we have seen how to obtain in a similar way the integration of h dot dl from 3 to 4 and from 4 to 1. Now, by adding the integration from 1 to 2 plus the integration from 3 to 4, we find that the term hy naught multiplied by delta y is positive along the path from 1 to 2, and it would be negative along the path from 3 to 4. So hy naught delta y would cancel from 1 to 2 to 3 to 4. But the term half the derivative of hy with respect to x multiplied by delta x multiplied by delta y is positive from 1 to 2, and from 3 to 4 it is negative multiplied by negative delta y, so it is positive 2. So the integration of h dot dl from 1 to 2 plus the integration of h dot dl from 3 to 4, its combination would introduce the derivative of hy with respect to x multiplied by delta x multiplied by delta y. In a similar way, we can prove that the integration from 2 to 3 plus the integration from 4 to 1 will introduce minus the derivative of hx with respect to y multiplied by delta y delta x. Now, by arranging the combination of 1 to 2 plus 2 to 3 plus 3 to 4 plus 4 to 1, we can obtain the integration of H dot dl over the closed path from 1 to 2 to 3 to 3, 4, 4, 1 equals the derivative of hy with respect to x minus the derivative of hx with respect to y multiplied by delta x delta y. And effectively, delta x delta y is the surface area included by this closed loop. Okay? Now, according to Ampere's law in its integral form, we say that the integration over a closed path HDL equals the current enclosed inside this closed path. So the current enclosed in this path is the current passing in the z direction. So the current enclosed in this path is the current density Jz multiplied by the surface area dx dy, or in other words, the current in z direction. So by combining the integration over the closed loop HDL equals the current, so we can say that the derivative of hy with respect to hx minus the derivative of hx with respect to y multiplied by delta x delta y equals Jz, the surface current density in z direction, multiplied by, the volume current density Jz multiplied by the surface area delta x delta y. Or in other words, if we are going to eliminate delta x delta y from the both sides, so we can say that the derivative of hy with respect to hx minus the derivative of hx with respect to y would equal Jz. We see that this is the y component derivative with respect to x minus the x component derivative with respect to y equal the third coordinate Jz. So the limit when delta x delta y tends to 0, the integration over the closed path h2dl over delta x delta y would equal the derivative of hy minus or the derivative of hy with respect to x minus the derivative of hx with respect to y would equal Jz. Following similar steps, we can prove that the derivative of hz with respect to y minus the derivative of hy with respect to z would equal gx, and the derivative of hx with respect to z minus the derivative of hz with respect to x would equal gy. And it can be noted that we are talking about the coordinates in arrangement such that here x, y, z, y, z, x, z, x, y. Okay, and if I'm talking about x, y here, so it is y, x here. If I'm talking y, z here, I'm talking about z, y here. And if I'm talking about z, x here, I'm talking about x, z here. Okay, so in general, we can say that the integration of a closed path h dot dl over the normal surface, regardless what is the direction of the surface, x, y, z, it would be the derivative of hz with respect to y minus hy with respect to z in x direction, which will equal the current density in x direction plus the derivative of hx with respect to z minus the derivative of hz with respect to x in y direction, which would equal the current density jy plus the derivative of hy with respect to x minus the derivative of hx with respect to y in z direction, which would equal the current density jz. So in general, we can say that curl or the rotation of the magnetic field H would equal the current density J. This effectively Ampere's law in its differential form. This form for the curl operator can be represented as a determinant in a simple form in the following form. So the first row would be the unit vectors ax, ay, az. The second row would be partial by partial x, partial by partial y, partial by partial z. And the third row would be the hx component, hy component, hz component. Let us make the first one, for example, if we are going to eliminate the first row and the first column. So the ax component would be partial hz by partial y minus partial hy by partial z, partial hz by partial y minus partial hy by partial z in x direction. If you are talking the y component, it would be negative partial hx by partial z, negative partial hz by partial x, minus partial hx by partial z, and already we have negative, so minus minus it would be positive, so positive partial hx by partial z. Finally, the az component would be partial hy by partial x minus partial hx by partial y, partial hy by partial x minus partial hx by partial y. So effectively, the curl operator, it can be represented as the nabla operator as a vector cross product with the magnetic field H. So the curl operator is equivalent to the nabla operator or the del operator cross product with the magnetic field H or the vector magnetic field H. This effectively is the curl operator in Cartesian coordinates. What will be the case if we are talking about other coordinates like cylindrical or spherical? So in cylindrical coordinates, the curl operator, curl of H would be 1 over rho, the derivative of Hz with respect to phi, minus the derivative of Hy with respect to z in the rho direction, plus the derivative of h rho with respect to z minus the derivative of hz with respect to rho in the phi direction, plus 1 over rho, the derivative of rho h phi with respect to rho, minus 1 over rho, the derivative of h rho over the derivative of h rho with respect to phi in the z direction. And to remember you, when we are going to make this differentiation, we first multiply h phi with rho and then make the derivative of this combination with respect to rho. The curl operator in spherical coordinates is 1 over r sine theta, the derivative of h phi sine theta with respect to theta, minus the derivative of h theta with respect to phi in r direction, plus 1 over r, 1 over sine theta multiplied by the derivative of hr with respect to phi, minus the derivative of rh phi with respect to r in theta direction, plus 1 over r, the derivative of rh theta with respect to r, minus the derivative of hr with respect to theta in phi direction. And as we mentioned before in the Cartesian coordinates, the rho component is composed of the derivative with respect to phi minus the derivative with respect to z. The phi component consists of the derivative with respect to z minus the derivative with respect to rho, and the z component is the derivative with respect to rho minus the derivative with respect to phi. Okay? Alright. Now, as an example, assume that we have magnetic field H equals 0.2 z squared in x direction for any point at z greater than 0 and h equals 0 elsewhere. So at z less than 0, h equals 0. It is required to calculate the closed integration of h to dl about a square path with the side d, so this square path of length d, centered at the point 0, 0, and z1 in the y equals 0 plane, so the plane y equals 0, where z1 is d over d, or in other words, z is greater than 0. So in this case, if I'm talking about HDL in a closed path, so it is the value of h at z, and z is equal d over 2, and the value of y is 0 in the plane y equals 0. So we are talking about the derivative. So we are talking about the value of h dot dl, and dl here we have the center at y equals 0. So we are talking about z from z1 minus d over 2 to z1 plus d over 2. This is a path along the z, and the other one is from z1 minus d over 2 to z1 to d over 2, and this along the z-axis. Along the y-axis, along the x-axis, we are talking about z1 plus d over 2. All this arm is z1 over 2, and all this arm is z1 minus 1 d over 2. So the arms in the z direction would be dz at z direction. If I'm going to dot product with ax, it would be 0. So the two arms along the z direction would be 0. Now the two arms along the x direction, one in the positive x, so it would be h multiplied by delta x, which is d in x direction, and this is the arm at z equal z1 plus d over 2. So we are going to replace z1 plus d over 2, z1 plus d over 2 with the value of z, and multiply this by the length along the x. So this is the magnetic field due to the upper arm, HDL. On the lower arm, the magnetic field is z1 minus d over 2, z1 minus d over 2, and the direction of this arm would be negative x, so it would be d, its length d, and it is in minus ax direction, so it would be minus. Now, by applying the value of z1 itself as d over 2, so this term is actually 0. So we only have the first term, z1 plus d over 2, no, already we have both terms, so we are talking about z1 plus 1 over d over 2 squared multiplied by d minus 0.2 z1 minus d over 2 squared multiplied by d. So in this case, it is z squared plus 1 over d squared minus z multiplied by d. So and this would be z squared plus d over 2 squared minus z1d, and we have minus minus, so it would be plus, so it would be z1 d squared multiplied by 0.2 multiplied by 2, it would be 0.4. And the other two terms which relate to z1 and related to d over 2 would be cancelled by the negative sign. Okay, so the integration over the closed loop in this case would be 0.4 z1 multiplied by d squared. And we can apply z1 to be d over 2. Alright, now this by using the integral form. By using the differential form, we say that curl h would equal j, and curl h in this case we have h in x component only, so it is 0.2 z squared in x component only, and we don't have y or z component, so 0 0 in y and z, and the curl operation in Cartesian coordinates ax, ay, az, partial by partial x, partial by partial y, partial by partial z, 0.2 z squared, which is the x component, plus 0 in y component, plus 0 in the z component. So in this case, we have the x value is 0, the y value would be the derivative with respect to x0 minus the derivative with respect to z, so it is partial by partial z, 0.2 z squared in y direction, and the derivative or the field or the magnetic or the current density G in z direction G, or the curl operator in z direction, the derivative with respect to x would be 0, and the derivative with respect to y would be 0 also, because this is function of z, not function of y. So we only have a component in the y component. So the magnetic field or the curl of the magnetic field in this case would be 0.4 z in y component only. Now by multiplying this magnetic field or the curl of the magnetic field by the surface area, so this is J multiplied by the surface area, which is d squared, we obtain that is 0.4 z d squared, and effectively the loop is located at the plane z1, so HDL in this case, or the current included in this case, would be 0.4 z1 d squared, as we obtained from the integral form. Okay, all right.